of my homomorphism, what this means is every point in the space X is moved at least this far by one of the generators. That's exactly what it's saying. And every point gets moved at least that far. So I'm going to say that the sequence phi I is divergent if this sequence of stretching factors is going to infinity. And this is really, I'm taking a limit with respect to my alpha filter again. Otherwise, I have to substitute. And otherwise, it's going to be non-divergent. So, as we've seen, you can have basically an arbitrary subgroup sitting inside of gamma. And this subgroup might act elliptically. Right? This might have bad orbits, or bounded orbits. So for example, here, I've got this ds23 star z. Under any acylindrical action of this thing has to have a bounded orbit. Right? So the actions don't tell me anything about this subgroup. But the fact that I have this subgroup here, well, clearly any homomorphism from G into the subgroup is also homomorphism from G into gamma. Right? And I don't really have any hope of saying anything about this for just an arbitrary subgroup of my acylindrically hyperbolic. But in this case, since H has a bounded orbit, all of these stretch factors are going to be uniformly bounded. It's going to be a non-divergent sequence of homomorphisms. So I really can't say very much at all about non-divergent sequences of homomorphisms, at least without additional hypothesis. I have to know something about my elliptic subgroups not being too terrible. I hope to say something there. Okay, but what we can do is for a general acylindrical hyperbolic proof, we can prove that in order to be, if you're not equationing Noetherian, the only way this happens is if this property fails on one of these non-divergent sequences. Right? So let me state that now. So suppose gamma acts acylindrically on hyperbolic space X, and for all finitely generated groups G, and all non-divergent sequences anytime I have this, I'm going to assume that all finitely generated groups create all non-divergent sequences, phi I factored through the limit map. Omega almost sure. So then my group is equation Noetherian. Okay, so just to remind you, being equating Noetherian is equivalent to every sequence of homomorphisms. Your homomorphisms factor through the limit map almost always. If you're acylindrically hyperbolic, then if you know that every non-divergent sequence already factors through, it follows that every sequence factors through. Right, so to fail to be equating Noetherian, it means you're failing for some sequence of homomorphisms that doesn't see the action sufficiently well. That's essentially what's going on here. So let me first, I'm not going to prove anything, but I do want to mention at least some of the basic ideas that go into this proof. I think this is a really nice set of tools. So before that, let me mention that, I mean, in theory, this simplifies this idea of proving acylindrical hyperbolic things are equationally Noetherian. In practice, this is still a fairly difficult condition to verify. So even in the setting of relatively hyperbolic groups that we have here, this is still a non-trivial problem to verify. But we can verify it there. And we have some other applications in mind where we're hoping to show that this works. So somehow this simplifies a very hard problem to a still pretty hard problem.
The notion of divergence, does it have any generators?
So these stretch factors do depend on the generating set, but I think the sequences going to infinity probably don't. That shouldn't matter, I think. So if you change generating sets, I think these things should change by some kind of amount. I believe, I'm gonna have to check that, but
It's just a triangle.
yeah.
Yeah.
Now, it does depend on this action, right? So you might have sequences that diverge for some actions and not for others. So the action you choose does matter here, right? And the action is in the statement, right? So sometimes it will matter that you choose a good action. That can change what's the routing, what's not. But the generating set for cheat shouldn't matter. And of course, as we now know, these groups have lots of these types of actions. So, right, I won't say too much about how to prove this, except a few of the sort of key ideas. One is you get a construction of call in. Just by the way these stretch factors work, you get a non-trivial, so that means no fixed points here, action of L on an R tree, which is just exactly the absence of cone of the space X with these constants as scaling factors. All right, so the fact that here every point is moved at least this distance by some generator is going to tell you that in this R tree, every point is moved distance at least 1 by some generator as well. And just translates directly to that. So this is now a non-trivial action. There's no global fixed points. And then acylindricity gives you the acylindricity of your original action. It gives you enough stability stability conditions. You get stabilizers of unstable arcs are finite in this setting to apply, Rip's theory, which says that this action on this R tree decomposes into specific pieces, specific types of actions on R trees, and then you can analyze that carefully with the shortening argument. Together with, in order to apply this in this setting, you also need to build JSK decompositions. And what the shortening argument ends up giving you in this setting, so here you have G mapping to L. The shortening argument is going to output some quotient of L, which is another gamma limit group, and also a quotient of G. And this quotient is going to come out such that if the maps that define S factor through, then the maps that define L factor through. Right? So if this was non-divergent, then we had already assumed they factor through and we're done. If it's divergent, we can repeat this procedure and get another shortening quotient and keep going. And the last thing is to prove a descending chain condition. Now this process eventually has to stop. There's no descending chain like this. And then once this process stops, you know that the last thing the maps have to factor through, and then you can pull it all the way back to the chain and mass flying out. Factor through. I will say this descending chain condition, we don't quite get it in general, so we end up using this assumption again in proving this descending chain condition. Right, so this descending chain condition also uses that these non-divergent mass factors through. Okay, so let me, how much time do I have left?
A few minutes.
A few minutes? Okay, good. So let me just do one more thing, which is try to give some sense of how you apply this in this relatively hyperbolic setting to get this implication. So first, if gamma is honestly hyperbolic, right, and these phi i's here are a non-divergent sequence, what it means is there's some point in this Cayley graph that's moved a bounded amount by every generator. And so if we conjugate that point to the identity, modulo conjugation, every generator here is mapping into some finite ball. So there's only finite many choices for what this is. Right? So omega almost surely, these maps are actually just constant. Passing to a subsequence, these maps are constant. And this limit group L is just some subgroup of gamma. Right? I just have it embeds as some subgroup. And of course, the limit maps factor through because I just conjugate to wherever that map is taking me. So in the relatively hyperbolic world, so now here I have G is hyperbolic relative to, I call my personal subgroup P. Of course, it can be a finite collection. I'm assuming P is equation Noetherian. I again have this set up. G is mapping my phi I to gamma. I have my limit group L. Now it's no longer true that L has to embed here as a subgroup of gamma. So things are a bit more complicated. It turns out what we can do is you can build a bigger group here called H, and a sequence of maps from H to gamma. So now we've got a sequence here, and then this is set up so this commutes. So we get a limit map from H to some other limit group M, where M is hyperbolic relative to a P limit group. Right, and you can see that limit group sort of naturally coming from part of the map from H to M. And you can also set this up where L actually embeds here. So L doesn't embed in gamma, but it does embed into this other limit group, which is hyperbolic relative to a limit group over your vertical subgroup. Right? And then, you know the part of the map that goes to this P limit group factors through appropriately, because you assumed P was equating Noetherian. And for the other part of the map, if you're hyperbolic relative to a subgroup, you're finitely presented relative to that subgroup. So there's only finitely many other relations that have to hold here, and finitely many things you're going to see after finitely many steps. And that allows you to get that map factors through. And then you can pull this all the way back to the diagram to get the corresponding map for L. This is in the non-diverging setting, so this is when phi I is non-divergent. We can do this. And then by our theorem, once you know this for non-divergent homomorphisms, we get this for all homomorphisms. Okay, so I'll stop here.
Any questions for Michael? If not, let's thank him again. And go for our final tea break.